So we'll start thermodynamics discussion. Okay, so here what exactly chemical thermodynamics? See, you will be studying same thermodynamics in physics also. So here I am saying it as chemical thermodynamics. So chemical thermodynamics deals with the heat energy exchanges, like heat energy changes during the chemical reactions. For example, from reactant to product, reaction like goes on right now. So now during this transformation, what is the energy change? Okay, that is what we are going to learn in this particular chapter. And you know, thermodynamics, see, it deals with study of heat flow or the type of energy that is flowing into or out of the system. Okay, system here, system means what? Whatever the chemical reaction taking place in any container or anything. So that is, we are considering it as a system here. Okay, so now thermo means what? Heat. Dynamics means what? Movement. So movement of heat, that is what we are discussing in this particular chapter. Okay, now thermodynamics deals with bulk properties. What I am saying? Bulk properties. What do we mean by bulk? Like large amount of substances. So thermodynamics applicable for macroscopic systems. It means it is a it deals with bulk. It means maximum, like larger amounts. Okay, now when it comes to smaller amounts like microscopic systems, so we will study that in statistical thermodynamics. That is not our in the part of our syllabus. Okay, so this is about the bulk matter, properties of bulk matter. Okay, and the next here when it comes to the rate of a reaction, how fast a chemical reaction is taking place, that is discussed under chemical kinetics part. This thermodynamics does not tells us about how fast a chemical reaction is taking place. It just tells us what? How much amount of energy is absorbed or released during a chemical reaction. That's it. Okay, and the reaction mechanistic steps also will be discussed here. Okay, right. Now there are some like what are the primary objects I have told you? It predicts the feasibility of a reaction. Feasibility means the spontaneity of a particular process, whether a process can happens naturally or not. If it is taking place naturally, we are considering it as a spontaneous process. For example, evaporation of water. So take some glass of water, you just keep it on a bench. What happens? After 2-3 days, if you observe, the quantity, the level of water decreases. So what happening there? Evaporation is taking place, but it is a slow process but happening naturally. Yes or no? So it is what? A spontaneous process, we can say. Or for example, like falling of water from high hilly region to down. What is this? This is also a natural spontaneous process, but reverse of it, we cannot say it as a spontaneous. It means reverse means what? Flowing of water from lower level to higher level. So that is not happens spontaneously or naturally. So we need to use some external aid, something like motors we need to use to take water from down level to top level. That's it now, right? So spontaneity means it should happen on its own naturally without any external aid. Okay, next, for a feasible reaction, calculating various types of energy changes and relating them to the reactants and product side, relating them each other. For a feasible reaction, determining extent of reaction under a given set of experimental condition. For example, if I take temperature as some 50 degrees, how the reaction is taking place. If I increase the temperature to 100 degrees, what is the change in the reaction? So all these things can be studied here for a feasible reaction. Next, it derive general thermodynamic relation. It means we are going to derive something like first law, second law and third law, where it gives relation between different terms. Okay, that is what we are going to see here. And before studying these things, we need to know some basic terminology that will be used in the thermodynamics. Okay, something like system. So what exactly mean by system? System means whatever the, for example, I am doing a reaction in this container. So now this container is considered as system. Okay, and the surrounding part around this system is considered as surroundings. Now together, the system plus surroundings, whatever the extra part we have, other part, so completely considered as universe. What is that? Universe. Universe means what? System plus surroundings. Now there is a portion, like there is a region, I can say imaginary boundary or a real boundary. Here it is a real boundary which is separating this system and surroundings is called considered as boundary. What is that? Boundary. It can be real or imaginary. Okay, sometimes some process might happen without any separation between real separation between system and a surrounding. So there we can consider it as an imaginary boundary. Okay, so we have three terms. One is system, surroundings and boundary. So for example, here you can observe, for example, here we have a kettle, I can say. Okay, so what inside of it? So we have some liquid inside of it, so that I can say it is a system. Okay, so now the remaining part can be considered as surroundings. Now it is separated by a imaginary boundary, this whatever you are up here seeing here, or a real boundary here you are seeing. See, real boundary, imaginary boundary means this glass part is there now, that is truly separating the outside part and inside part, right now. So that is a real boundary. But whereas inside, if you observe the layer here, the top layer of this whatever the liquid we have like this. So now this extra part is there. Now there is nothing now. So only this liquid is there, this extra part is there. Okay. So now that is separated by imaginary boundary here. Okay, like that you can observe. So now what I am saying, there are sometimes terms system, the part of universe under our observation or under thermodynamic investigation is considered as system. Okay, and after that surrounding means everything includes except the system or the part which is under our observation. Okay, now this boundary is there now. So this boundary is again sometimes that system so takes heat energy into the system or it will be releases. Okay, now we need to classify the system into different types. So system is classified as different types. So I am saying here system is classified into different types like open system, closed, and other one is isolated. Okay, so open system means now the system can able to exchange heat and matter also. It can exchange both heat and exchanges both heat and matter between system and surroundings. So give one simple example, like a cup of tea which is kept over here. What happens? Now some part of that heat is going out. Again matter can also be whatever the liquid is there, that can also be exchanged with the surroundings. Yes or no? So that can be considered as open system. Now simple example you tell me, like our human body or any animal body you can consider. So whether it is open system or closed system? It is open system. Okay, remember that. Okay, like sweat comes out now. Okay, so it means that fluids also exchanging and heat is also exchanging. So we can say it is a open system. Okay, right, this is again important one. Next, what about closed system? There is only exchange of heat only, but not matter. Only what it takes place, only exchange of heat but not matter. So something like a bottle with closed cap, right now is there any exchange of matter? No. Matter won't comes out, but heat can be transferred from inside to outside like that. Okay, so that is considered as closed system. Now what about isolated system? No exchange of heat and matter, both cannot be exchanged between system and surroundings. Okay, so here the simple example I can say is thermoflask. Like actually thermoflask also after certain time it will also loses its heat, but to some extent, to some particular time, like for example around 1 hour or 2 hours, some thermoflask will retains its heat and the matter inside of it without any exchange or very negligible amount of heat exchange. Okay, so for our understanding purpose we can say thermoflask as an example of isolated system. And you can also remember universe is the best example of isolated system. What I am saying? Universe is the best example of isolated system. So what I told you, system plus surroundings is considered as universe. Okay, so universe is system plus surroundings. Now what I am saying, universe is a best example of isolated system. Okay, remember this. And the next, here we have boundary. One is diathermic, another one is adiabatic, I am saying. So diathermic means what exactly? So it can able to exchange heat. So it is conducting. It means able to exchange heat to the system to surroundings or surrounding to system. Whereas diathermic, adiabatic means what? It is a non-conducting. Therefore there is no exchange of heat between system and surroundings. Okay. So now due to this nature, now what happens? System divided into three types. What are those? Open, closed, isolated. Okay, clear now? Those things are clear now? Next we will discuss. Now thermodynamic properties. So what I am saying, thermodynamic properties. So whose properties defines a system completely. These are of two types. One is extensive properties. These are important again. Extensive properties, and other one is intensive property. So what exactly extensive properties are? So these, see here, what is there now? Here intensive. So you can just remember intensive, independent. So quantity, or you just remember mass. Independent properties are intensive properties. Okay, and these are mass or quantity dependent properties. Quantity or amount of substance, mass dependent properties. Give some examples for mass dependent properties, like examples. Okay, before going to give examples, you can also write a few more points. These are additive. This can be added, additive, and divisible. Okay, examples you can write something like amount of substance, like mass I am taking, like grams, kgs, whatever you are saying. So now volume I am saying. See, volume of a liquid. For example, here I have this bottle containing half of the bottle is filled with the water. So now what is the volume of water? What is the quantity of water? Half liter you are saying, because it is a full like 1000 ml bottle, filled half of it. So means you are saying so now this volume is like depending on what? The quantity, how much quantity of water present in it. So that is what quantity dependent properties. Now volume is a quantity dependent property. For example, we are going to market and we are taking some 15 or 10 tomatoes. So now 10 tomatoes having weight of 1 kg. Now I am taking only 5 tomatoes. What is the quantity of, like 5 kgs means it might be around half kg, around, I am saying approximate, just for understanding purpose. All of them having same size, you can just remember like that. So now as quantity is changing, what happens to the mass? It is also changing now. So now mass or quantity dependent properties are considered as extensive. Now weight or amount of substance is a quantity dependent. Here I can say it is an extensive property. So I am writing mass, volume, all this comes under extensive properties. And next you just tell me some other properties that you know, like number of moles. I am saying we will be using the number of moles. What about this number of moles? Number of moles also. If I say 12 grams of carbon, you are saying 1 mole of substance. If I say 15 or like 24 grams, again you are saying 2 moles. As amount increases, quantity changes, number of moles also varying, therefore number of moles is a quantity dependent property, so I can say it is an extensive property. Is this clear or not? Right. Okay, next give some more examples, like number of moles, mass, volume, and you know these things are there, something like we will be going to study them, about them. Enthalpy, entropy, internal energy U, and then next Gibbs free energy G. All these things, all free energy functions comes under extensive properties, just remember them. Okay, measurable again. Okay, next what about these intensive properties? Give some examples for intensive properties. Quantity dependent, mass dependent properties are considered as intensive property. And one more point you can remember here, these are not additive and not divisible. Okay, and next one is the ratio of two extensive properties is an intensive property. Okay, write these things. The ratio of two extensive properties is an intensive property. Okay, so now tell me what are the relation like things you know. See, for example, I am saying temperature. Tell me, temperature will be extensive or intensive? Temperature is an intensive property. For example, I am saying boiling point of water is how much? 100 degrees. Whatever the quantity you are taking, whether you are taking 1 liter, 10 liters or 1 drop, 2 drops, boiling point of water will be remains same right now. So boiling point is an quantity independent, it is not depending on how much amount of water you are taking. So I can say it is an independent of mass or quantity. So I can say it is a intensive properties like boiling point, melting point, okay, and freezing point, all this comes under intensive properties. Next, one more thing I told you, ratio of two extensive properties is an intensive property. For example, density. So tell me, density means extensive or intensive? Just remember, whenever someone asks you density of water, they will ask, but not density of 1 gram water or 1 liter water, 500 ml water, right now. So they will just say density of water. What are the units? Gram per ml or kg per liter, like that they will mention right now. So now what again I am saying, density means what? Density means mass by volume we are writing. So mass is an extensive property, volume is also extensive property. Ratio of two extensive properties is an intensive. So density is what now? Density is what? Intensive property. And what about pressure? Pressure. So here we have force per unit area. So P by F by A I am writing. So now here force is an extensive property. What about area, you tell me? Area. It is also quantity dependent now. If I have only smaller quantity, it will occupy lesser area. As quantity increases, area occupied also increases. So area comes under what? Area, length, volume, all this comes under what? Extensive properties. Ratio of these two things. Now pressure comes under intensive. Pressure. Okay, so you can remember this. And now here I am writing surface tension and refractive index. This will be specific value for particular substance, okay, which comes in physics again, okay. Surface tension, refractive index, and viscosity, etc. All these are what? Intensive properties. Okay, so here I am saying molar heat capacity. Tell me. So heat capacity, when I say heat capacity, you can write extensive. Molar means per mole we are saying. So whenever we are taking ratio, that is comes under intensive. Remember this. Okay. So simply they will ask which of the following is are extensive and intensive properties from the 4 options. Okay. You need to ready to answer them. Okay. And the next over this one. Next, we have one more term like state of a system, or which is again divided into 2 things. One is state function and other one is path function. So what exactly state function means? So here these properties are independent of path followed. They only depends on initial and final state of a system. Okay, and here they depends on path followed to achieve final state from initial state. Okay, for example, work is a path function I am saying. For example, I am giving you some work. For example, you need to carry some load of luggage from this 3rd floor to ground floor. So you can directly go like this. So now here the amount of work you are doing will be less when we compare with the work that you are doing from going outside and going from the staircase. So it is depending upon how you are following the path right now. So work is a path function. Okay, so work and heat, these are the 2 examples of path function. And what about state function? It is independent of path followed. It depends only on initial and final states. Something like temperature, pressure, volume, all these things are considered as state functions. Temperature, pressure, volume, and this enthalpy, entropy, Gibbs free energy, and internal energy, all these things comes under what? State functions. Okay, write these examples. So these are the symbols. So these are the symbols we are using to express the different thermodynamic properties. We will discuss one by one later. Okay, as of now you write this. And next, thermodynamic processes. Okay, so first one is we have isothermal process. So what exactly iso means what? Same. Thermal means temperature. So same temperature, it means temperature constant. If something is constant, change in that thing will be 0. So change in temperature will be 0 in isothermal process. So T constant, dt will be 0. Okay. So now the graphs which we are drawing at constant temperature are called isotherms. What I am saying? Isotherms. Okay. So for example, P versus V I am writing. So the graph will be something like this. Like this. Okay. So as volume increases, pressure decreases, you can remember. So P is inversely proportional to V. Okay. And if I want to draw P versus T, tell me what is constant here? What is constant here? Temperature is constant now. So you need to draw a line like this. Temperature kept constant, should draw like this. Okay. Now if I am saying V versus T, so tell me how can I draw the graph? Tell me what is constant here? T constant. It means you should draw a line keeping your temperature constancy, as throughout the process temperature having only one particular value. See, throughout the process temperature is having a fixed value, but pressure is increasing from here, here. Pressure values are increasing now. Here also temperature is fixed, whereas values are increasing, like that. Okay. Next, isothermal is over. Next one is isobaric or isochoric. So isobaric here, what is constant? So bar is a unit of pressure. So iso means same pressure. So pressure constant. So dP will be change in temperature will be 0. So the graphs here drawn at constant pressure are called isobars. Okay. So P versus V if I want to draw. So what is constant here? Pressure. So how can I draw the line? Like this. Okay. And V versus T I am drawing. So with increase of temperature volume also expands. Okay. So something like this. Like this. Okay. With increase in temperature what I am saying, volume also expands. So you should draw it like this. Okay. If I want to draw T versus P, tell me how can I draw? Like this, right? And next graph is what? Isochoric. So what is constant here? V constant, so dV will be 0. Okay, change in volume will be 0. So now P versus T, what happens if temperature increases, pressure also increases. Like this. If I want to draw V versus T, what is constant? Isochoric means V constant. So your graph should be parallel to what? Parallel to this temperature axis, x-axis. Okay, right. So you got it now? Drawing the small graphs. How can I draw this? To what?
Y-axis.
So parallel to y-axis, like this. Okay, draw this. This one. So just take any generalized application. Just imagine as volume increases, what happens to the pressure? Pressure. Pressure means what? Force per unit area. Okay, if volume increases, that what happens to the area? Volume increases, area also increases, na? So force per unit area decreases. Okay, you can understand from the definition at least. So next process we have is fourth one, adiabatic process. Here no exchange of of heat between system and surroundings. So what is constant here? No exchange of heat means Q. Q is constant. Q indicates heat constant. So dQ will be 0. Okay. So graphs about the graphs regarding adiabatic process I will tell you while discussing about complete discussion of adiabatic process. Okay. And next one is, write this. Okay. After this you need to know some basic difference between, there are two types of process. Previously we discussed thermodynamic process. What are the process we discussed? Isothermal, isochoric, isobaric, adiabatic. These are the four processes we discussed. Now these four processes can be happen in two ways. One is reversible, another one is irreversible. So what exactly mean by reversible here? See, for example, I have a system here, I have a cylinder here like this. Okay, to this cylinder we have one piston here. Okay, that can be moved up and down easily without any forces. Okay, so here I have some gas inside this cylinder. So now what happens if pressure of gas, see every gas has its own pressure, right? So P gas I am saying here, or P internal I am saying, and here outside of this cylinder, this piston, P external. So now what happens if internal pressure is more? What happens to the piston? Moves upward. Okay, if external pressure is more, moves down. If both pressures are almost equal, stays at same position. Now just imagine there is very slight increase in internal pressure. What happens to the piston? Slowly it moves upside, again it will stays there. Okay, so now reversible process happens when there is very slight difference in their pressures here. Okay, so now reversible process is a hypothetical case. What I am saying? Hypothetical. Whereas irreversible process is a real case that is happening in the natural nature. Okay, so now look at here, it takes place at infinite number of small steps. Okay, so and it would take it infinite times to occur. Okay, it is a very slow process. Okay, next, it is an imaginary and it is assumed in the presence of frictionless, weightless piston. Okay, now it is a state of, it is in the state of equilibrium at all the stages of operation. Yes or no? I am saying this equilibrium, this like thermodynamics, I mean this piston is at equilibrium, this process is at equilibrium at all the stages. Why I am saying it equilibrium? Because the internal and external pressure is almost same now, so that's why it is almost at equilibrium in all the cases. Okay, now all the changes are reversed when the process is carried out in the reversible direction. It means I am saying slight increase in internal pressure will move the piston upside. Similarly, I can reverse the process by slight increasing external pressure. The process can be reversed. Like this, all the steps can be reversed by having some external like opposite force with slight increment right now. And see, it is extremely slow. Okay, and comes to this, it takes place in a single step. For example, here P internal, P external have large amount of difference in pressure. What happens? Piston will suddenly moves upside or downside. Okay, like depending upon pressure values for both of them. So now we cannot reverse this, it will be having sudden increment, right? So it cannot be reversed. So whatever the process taking place in the nature are irreversible process. Okay, so just now we discussed about that falling of water from hilly region to down. So it is a one side process, it is a irreversible process. Do you got what I am saying? So for making it reverse, you need to use high external aid like motors and all. Okay, but it is reversible, it is a real and can be performed actually. Okay, so equilibrium state only attained at the initial and final stages of the operation. After occurring the process changes do not return to the initial state by themselves. It cannot happen by themselves, like gaining its the original or the previous or the initial stage from the final state cannot be like attained on its own. Okay, by using some external aid it may be possible. Okay, so now this process proceeds at a measurable speed. Okay, now here what you need to know is the work done is reversible process will be maximum in all the cases. What I am saying, the work done in reversible process will be maximum when we compare with the irreversible process. Okay, remember this. Okay, now I am saying isothermal what we discuss, isothermal process we discuss, adiabatic process we discuss. Now we have isothermal reversible process and isothermal irreversible process. So before going to discuss about these things, these terms, we need to know some other terms and basic first law and zeroth law of thermodynamics. First of all, the basic term you need to know is internal energy. So what exactly internal energy? So internal energy indicated with the symbol U or E. Sometimes U or some books gives E. Okay, so internal energy is a state function. See, every system whatever you want you take. So every system has energy associated with it internally, right now. So it is nothing but internal energy is nothing but sum of all types of energies of system. For example, I have a system here, okay, like a water molecule or whatever you want you take. Okay, so now that that system has something like rotational energy, that molecule will keep on rotating now, so it will be having E rotational, and these bonds are there now, here bonds, the bonds can get vibrated, so I can say vibrational energy, and the bonds can like I can say translate. Okay, I can say so E translational, okay, E rotational, vibrational, translational, like this. E bonding energy, bond energy I can say. Like this we have different number of energies. All these are we can say at microscopic level. The sum of these all energies will be considered as its internal energy, U. Okay, so U in simple words I can say total kinetic energy plus potential energy plus all these things. Okay, right. Now the internal energy U, the exact value of U cannot be calculated. What I am saying, exact value of internal energy cannot be calculated. Why? Because it is associated with very microscopic energies also. Okay, so these energies changes even if we change a little in the temperature. So they keep on changing the values. Therefore, exact value of internal energy cannot be calculated. Okay, but change in internal energy can be calculated. So what I am saying, you cannot calculate U, exact value of U, but you can calculate change in internal energy, U, delta U. So this delta symbol indicates what? Change in internal energy. Now what I am saying, internal energy is a state function. It depends on initial and final state. Okay, it is independent of path followed. Okay, now right, so delta U we got. Next, we will discuss about first law of thermodynamics. So what is this first law of thermodynamics? Tell me fast. Any idea? The total energy of the universe will remains constant. Okay, so now the energy can neither be created, can be created nor be destroyed. This is a basic definition of station, but can be converted from one form to another form. It means the total energy of the universe remains constant. That is, the total energy of universe remains constant. This is the first law of thermodynamics. Okay, you can remember this line. Okay, so now for example, I have a system having, this is a system having U1 amount of energy. It means that is the internal energy of that system. Okay, so now I am supplying Q amount of heat to this. Okay, so now what happens? Its internal energy becomes U1 plus Q, U1 plus Q. So now I am doing some work, W amount of work on it. Therefore, its internal energy becomes U2. Okay, so now U2 is equals to what I can say, U1 plus Q plus W. Yes or no? So now U2 minus U1 is equals to Q plus W I can write. So this is a mathematical equation of first law of thermodynamics. So this is changed now. So delta U, change in internal energy, delta U equals to Q plus W I can write. Okay, so delta U is what? Change in internal energy. Q means what? Heat supplied, and W is work done. Okay, so now delta U equals to Q plus W we got. Okay, so W means what? Work done. Okay, about work done we will discuss in the next class. Okay, so yeah, you can write this, further we will discuss next numericals also. So numericals related to this we will discuss in the next class. Okay.